Okay, friends, so let's work on hypotheses first. We need a null and we need a research. All right. With a test like this one, where you have an idea of what might be going on with the study, sometimes it's easier to start with the research and then reverse engineer the null from that one. So in this one, the researchers want us to believe that the vaccine is lowering flu rates. Now, when I say lower, statistically significantly lowering. Statistically significantly lowering. We know it on the sample anyway, it lowered it from 12% to 10%, but that might not be statistically significant. That could have been just random chance. So, is it statistically significantly lowering the flu rate? The null would be that it doesn't. But there's a more efficient way, of writing it than this, than writing out these sentences. And it brings in the variable that we're about to test today. The variable we're going to test is a percentage. We have one of those already. It's p. It's a little p. Little p, that's a little p, not a big P, not the big P value. That's little p from the population proportion. This is going to be the flu rate of those on the vaccine. We're testing that. We're trying to see if it is statistically significantly lower than without the vaccine. So we can actually say this entire sentence without having to write a sentence. We can just say we think the flu rate is statistically significantly less than 12%. That's not bad at all. Which means the null has to be everything else. Now, technically speaking, it's easy to say it's greater than 12%, but you should also include equal to. Two numbers are either less than, greater than, or equal to. So this is the mathematical statement of the hypotheses. The interpretive statement of the hypotheses is, if this is the flu rate of those on the vaccine, the research hypothesis is that it's significantly less than 12%. The null hypothesis says, no, it's not. It's either the same as 12% or your vaccine makes it worse. Hope that doesn't happen. So those are the hypotheses that we're going to test in this first example case. So we can always set up the hypotheses for a proportion by using little p. Now, how do we actually take a look to see which one to believe? Okay, we're going to look at this two different ways. Okay, my dear friends, the first thing we have to do, no matter how we choose to attack the test, is we have to build the null sampling distribution. That was kind of the first bell curve last week that we compared the p-value against with little asterisks. And then I realized I actually have the exact right tool to do this with, a gift one of my former students gave me, a 100-sided die. Thanks, my friend. It's actually a perfect way to simulate a 12% flu rate. I can roll this 100-sided die one time for each of 500 people. And if the number comes up 12 or less, then that means that person has the flu. And if it comes up 13 or more, that means they don't. No problem. So I'll start rolling. And as I learned after trying about 5 or 6 times, it is absolutely a huge pain in the ass to try to collect data off a 100-sided die. I'm not even sure how to roll it. I was bouncing it off walls and anyway. And then it hit me. I've got a way more efficient 100-sided die at my disposal. And that tool we're going to use is Microsoft Excel. This way we can roll as many 100-sided dice as we need, and we can do it simultaneously, which is great. Okay, so let's take a look. First of all, over here is in rows 1 and 2, we've got people from 1 all the way up to 500, if you scroll way over here, 500 people. And then we've got their status, whether they have the flu or not. Now, how are we deciding? Right there, my dear friends, is the 100-sided die. It's going to generate a random number between 1 and 100, just like our 100-sided die. And then if it comes up 12 or less, they're going to have the flu. And if it comes up 13 or more, then they're not going to have the flu. Beautiful. Now, it's going to be a pain to check all those people as we scroll to the right. So we're going to keep track of that right here in this cell. That's going to tell us how many people have the flu at this particular juncture right here. Now, also, I've included this handy dandy graph right here, which is going to graph the results as we do them over time. So right now, there's only one spike in this graph, and that's because in that particular sample of size 500, 60 people got the flu. Now, one more reminder. This is the null hypothesis sampling distribution, which means we are assuming that these people are not vaccinated and or the vaccine isn't doing what it's supposed to do. Those are two equivalent statements. If the vaccine's not working, then it's just as useless as not taking it at all. So we're assuming the vaccine is ineffective or we're keeping track of unvaccinated people. Okay, let's sample 500 more. So I'm going to roll that die 500 more times. All right, that time 58 people got the flu. So you can see that second bar just popped up on the graph. Let's do them again. Okay, that time 70 people got the flu. That time 70 people got them again. So you're seeing the graph is starting to build itself. That time 66. That time 66 again, 53. Okay, so I think what we need to do now is we're going to let this graph build and fill itself out. It's going to eventually create a certain curve that you're used to seeing in our class due to the central limit theorem. You probably already maybe guessed, ooh, wait a minute. ADD just got the best of me. Why is that bar red? 47 people got the flu. Why is that bar red? Why is that bar red? Write down your idea right now. That's going to be question number 2 on your homework. And we're going to come back and answer it. Okay, now whatever you wrote is great. Don't change it. The reason that bar is red is because that's a result that agrees with what the study got. Remember, the study got 50 people that got the flu out of 500. We're trying to see if that's surprising. Well, if 50 is surprising, then 47 would be even more surprising. That's even less than 50. You might remember the formal definition of a p-value. It's the chance of getting your data, or even more extreme data, assuming the null hypothesis is correct. So, if 50 out of 500 is surprising, 47 will be even more surprising. Well, let's see if we can generate one more red one, and then we're going to let this thing go and run for a while. 64 is not below 50. 63 is not. 61 is not. 59, 68, 54. Let's just see. Man, maybe this is supporting the research hypothesis, because we've only seen so far one data point that is equivalent to what we saw in the study or less. Man, there's a lot of gray showing up there. All right, we're not going to get another red one. Well, you know what that means, friends. It means I got to find myself a stapler, hold down this F9 button, and let the curve build, and then we'll come back and chat about it. Let's do that now. Hey, I just realized something. First of all, you're probably seeing the beginning of a bell curve, but there's also really no need to have this axis stretching out all the way to 500. I mean, if you got a 12% flu rate, chances are you're not going to get much more than about 125 people, if that. So let's format the axis so that it only goes out to... There we go. 100 looks pretty good. Now what I'm going to do is I'm going to keep re-randomizing, and you're seeing that bell curve pretty well. Still got some little holes in it here and there, so let's just let the Excel sheet keep rolling dice. I think we've seen enough trials now, my dear friends. And what you're seeing a bell curve, just like hopefully you thought you would. Central limit theorem says it's going to be there in the background. It's always kind of fun to see it organically show up, though. Now, what are all those red bars? Well, those red bars are all the instances where 50 or fewer people got the flu out of 500. So it looks like somewhere around almost 300 people, 271 people got it 50 times, and so forth and so on and so forth and so on. So if you look at the entire curve, there's not a whole lot of area that's in the 50 or fewer. So
from last week, we would have put a red asterisk right here and said that's where we landed in our data. So the question is, what is the chance that we would have landed there or even further left, because that would be more surprising, assuming that the vaccine was ineffective, which means assuming it wasn't doing what it was supposed to do. So what we can do now is we can pull this graph down, and I've actually kept track of this up here. So the number of cases where 50 or fewer folks got the flu, I've actually got Excel tabulating this right here. It was 1,194 samples. Now, each sample is 500 people, so you can see the amount of time Excel just saved us by doing this, so that's great. How many total times did I run the study? I ran it 13,162 times. So the chance of a lower flu rate, meaning that 10%, remember that 10% we got from the sample study? Based on chance alone, there's about a 9% chance that we would have seen that lowered flu rate, even if the vaccine were completely ineffective. Said a different way, roughly 1 in 11 samples would show us a flu rate like we just saw, even if the vaccine weren't working. I'm going to ask you about how I got that 1 in 11 on the homework as well. It's not a statistical question, it's an arithmetic question. Now, what does that p-value tell us? 9%. 9%. Well, if we use 95% confidence, it tells us that we have not escaped the 95% confidence interval. It tells us that we have a p-value bigger than 5%, so we're still contained completely within the 95% confidence interval. So if we got a big p-value, which is what this is by 95% confidence, this is a big p-value. That tells us, my friend, that we should believe the null hypothesis. In other words, it does not appear as though the vaccine is significantly lowering flu rates. We have not seen enough statistical significance. Yes, 10% is less than 12%, but it hasn't escaped the confidence interval of the null hypothesis. So we'd have to conclude right here that this flu vaccine does not appear to be working based on a sample of size 500. Okay, now I'm not going to make you run a Monte Carlo simulation every single time you're going to do one of these things. And I bet you got a ton of questions right now about the process for hypothesis testing that's a little less ethereal than that may have felt. So next video, I'm going to show you a template sheet that I've come up with over the years that really seems to help students be able to knock out hypothesis testing. And well, let's just get to the next video and take a look.